I think we can get started now. Um, Hopefully you can all hear me okay. So several of you may have noticed that there is a question that's been put in the chat window. So I guess we're going to start with that. Depending on how long that takes to answer, there's a fairly good chance that the quiz that is scheduled for Friday will have to be pushed. But we'll see. We'll play this a little bit by ear, and I may not even make the decision until Friday. But let's spend some time talking about this first project. So the question that is asked um, is focusing on not being entirely sure what the code is supposed to do, and asked specifically, is the code supposed to return a data set and you need to interpret the data? And the quick answer to that question is no. So ultimately, what Project One is asking you to do is implement naive Bayes. And now the question becomes, what is naive Bayes? Well, so this is an example of supervised learning. Where in particular, you're doing classification. All right. What do I mean by that? So you have 5 data sets that have been specified for you to work with. And when you look at those 5 data sets, each one of them has a field identified that corresponds to a class label. And the goal is to take any data point from that data set that does not include the class, run that data point through your naive Bayes classifier. Boy, that looks a whole lot prettier on the whiteboard than it does on what you're seeing. Anyway, um, and then return the class. And you want it to do it as accurately as possible. So you have 5 data sets. And I've actually asked you to generate an altered version of each of those data sets, where the altered version is taking 10% of the features and shuffling up the data within the data set, which is essentially introducing noise. You are also asked to do tenfold cross-validation. So what that means is for each of those now 10 data sets, you're going to run 10 experiments. And so that means over the course of the entire project, you are generating 100 models and then testing each of those models. So that's okay. So what do the models look like? The models consist of estimates of the class probabilities, as well as estimates of the conditional attribute, the class conditional attribute probabilities. And then once you have estimated those probabilities for each of these 100 trials, you will then take whatever the held out data set is and run it through to generate the classifications for those held out examples and compare the results against the ground truth to see how well you're performing. So Ryan, does that answer your question? And if not, feel free to ask more. That's correct, but you have 10 models times 10 different data sets, which is why you end up with 100 models. So 10 models per data set. Does that answer your question, Nathan? Are there any other questions related to the project before we move on? You have 5 data sets unaltered, and then you have 5 data sets where you have altered the original ones. 5 plus 5 is equal to 10. Any other questions? Well, here, let me do this. So this is showing the list of the 5 data sets you're supposed to use. The breast cancer data set, GLASS, IRIS, the small soybean data set, and the congressional voting record data set. So those are the 5 data sets you're starting with. When we look down here, this talks about 2 different versions of these data sets. The first one is just the 5 that you get off of the repository or out of Brightspace, however you get them. But then this is the thing that is describing how you will alter those data sets. So you go through, select 10% of the features at random and shuffle the values. Once you've done that, you now have a different data set, and that's where you get 5 additional data sets. Nathan, does that help? Okay, cool. Any other questions on the project? Okay, then let's move on. And actually, this is relevant with the current topic, because you may recall that one of the things that we said when we were talking about naive Bayes is that naive Bayes makes its decisions or classifications based on Bayes decision theory. And at the time, I gave you a very quick overview of exactly what we were going to do with Bayes decision theory. Well, what I want to do today is spend more time and go through this in a little bit more detail. It's still not going to be terribly detailed, but to give you more of a sense of what's happening here. And to do this, I'm going to restrict the discussion, at least for now, where I'm going to say, let's assume that we are trying to decide between 2 options. So putting this in the classification context, up until now, we've spent a lot of time kind of putting all of the algorithms in a 2-class classification context, where you look at a data point, it's either a positive class or it's a negative class. Now, in your project, you're going to be looking at data that has more than 2 classes. But here, this is still consistent with what we've talked about so far. So think of this as 2 classes. All right, what we're going to do for this is that we are going to start by denoting the choices, or denoting our options, as A1, and A2. So you can think of these as the ground truth options available to us. We can put a data point in A1 or we can put a data point in A2. And then we will denote our choices as alpha 1 and alpha 2. Now, what's the difference? Alpha 1 is what the classifier says that the example belongs to, when in reality, it either belongs to A1 or A2. And so part of what we're interested in is whether or not our choice of alpha 1 or alpha 2 is correct. And more importantly, what does it cost us when we're wrong? And we are going to make choices to make our choice based on evidence that will denote E. Now, what is this evidence? Think of that as the feature vector or the attribute vector. This is the vector of inputs that we get from our data point. You know, if we're talking about things like color or size or orientation or whatever. All right, so this is the main notation that we're going to work with here. Well, there's one other thing I have to define notationally. And excuse me, and this notation is a little bit different than what you've seen so far, because what we want to do is consider the cost or the loss associated with a choice, which we will denote lambda of alpha sub I. So that is the choice that the classifier, for example, would be making, given the correct option was A sub j. And what we'll see in a minute is that there are going to be cases where I equals j. All right. So with this notation, we will then define expected loss and we will also refer to this as risk as the risk of our choice alpha sub I given the evidence, which will now be equal to the sum over j, and j will end up summing to the number of options that we have of lambda alpha sub I given a sub j times the probability of a sub j given the evidence. All right, let me pause there for a second to see if there are any questions with the notation. Okay, I'm not seeing any. So intuitively, if we are making a choice based on some evidence, which I'm going to denote alpha of E, that's the choice based on the evidence, then what we want to do is choose by minimizing the risk. Right? Any questions about that? Okay, so what I'm going to do now, this is actually the general formulation of the Bayes decision theory problem. But what I'm going to try to do to add a little bit to the intuition here is I'm going to simplify this down quite a bit, but recognizing that with one particular loss function that you're probably going to use quite a bit, it makes a little bit of sense. All right, so I'm going to go to a new page.
New page.
Now remember that we're working for purposes of example with this two-class problem. I'm going to simplify some of the notation. Where I'm going to let lambda sub ij basically be equal to lambda alpha I given aj. And again, I do this only so that I don't have to keep writing that long expression out. And as you'll see in a minute, I'm going to simplify it even further, where we will let lambda I equals 0. Make sure I'm not lying to you. Yep. And lambda ij equal 1 when I is not equal to j. So in other words, what I've just told you that we're going to use here is 0-1 loss, which again is a common loss function that you'll be using. All right. So now let's consider our two choices, where we can define our risk for each choice this way. Now, at the moment, these two expressions are still written in the general form. If you plug in the 0-1s that I have up above, then you'll notice that the bottom one, or I'm sorry, the top one just becomes that, and the bottom one just becomes that. Okay. Because we're minimizing, here we would choose alpha 1 if the risk of alpha 1 given the evidence is less than the risk of alpha 2 given the evidence. Okay? Well, the way I'm writing this is deviating a little bit, but it'll still work. If I plug this in from above using 0-1 loss, notice that that gives us probability of A1 given the evidence less than probability of A2 given the evidence. But this is a little bit uncomfortable, except when you remember that what we're looking at here are the choices or the options rather, that are incorrect. And so there's also the thing, how do you deal with this probability distribution? So what we're going to do is we're going to apply Bayes' rule to these. And when we do that, now we get oops, oops, oops. We get this inequality. All right, well, the first thing to notice when looking at this inequality is that we don't need the denominator, right? In fact, if you want, you just go ahead and multiply through, which will give you probability of E over probability of E on one of those sides, and that just becomes 1, and it drops out. Okay. So what do we have here? Let me see. Did I skip something that I shouldn't have skipped? Eh, not really. I guess we can still go with this. Where, actually, yeah, I mean, I did skip a bunch of steps I probably shouldn't have. So what I'm going to do is I'm going to post a separate document that shows those missing steps, because in the process of doing all of this, what you're going to end up with is you're going to maximize the probability of A given the evidence, which can then be rewritten as the probability of the evidence given A times the probability of A. And where that comes out, and this is where I'm trying to figure out where I screwed up by skipping those steps, the inequality should have flipped. Oh, I know where it screwed up. I should have actually plugged in and expanded and then broken out the common terms. And then you would have seen it show up. All right, anyway. So this is what ultimately leads us to the naive Bayes rule of maximizing that product, where the probability of C here is corresponding to the probability of A1 or A2 above, because that the C is your choice or the class, and then the conditional probabilities correspond to that evidentiary probability shown in those inequalities. Right. Again, I will upload a better written description of what's going on here that doesn't jump steps. So before I do that, are there any questions? My mistake was I was trying to make up time, and I probably should not have done that. All right. So now we're going to shift gears and go back a little bit to the topic that we had earlier when we were discussing inductive bias.
New page.
And to do this, I need to give you some definitions. When I learned my lesson, I'm not going to skip steps. All right. So your first definition, a hypothesis, and remember, in this context, when we use that word hypothesis, think model, is said to be consistent with a set of training examples E, which we are drawing as a subset from some sample space X, if and only if, when we apply the hypothesis to, as you'll see, every example in E, that it equals the true class. In other words, a consistent hypothesis is always correct on the training data. Don't worry about the potential issue of overfitting. That's something else that we will need to address, but for now, just use this as our definition. Okay. Here's where things start to get a little bit abstract. The version space for some hypothesis space H given examples E and denoted VS of H and E is the subset of hypotheses in the hypothesis space H consistent with E. All right, so the first thing to take from this definition is that there is an assumption that if I have some set of examples, some set of training examples, and I'm going to apply a learning algorithm to them, that there may actually be several possible models consistent with that training set. Now, you'll remember that this is where we started talking about things like the representation bias, because what the representation bias does is it defines H. It will identify out of the set of all possible ways that you could formulate a hypothesis or a model, a subset of those models that conform to the representation that you've chosen. And then when we talked about a preference bias, what that does is it selects a hypothesis H from the version space. In other words, rather than just having this entire set of hypotheses out there, it allows you to pick which one you want. Okay. Any questions about that so far? All right. So now what I'm going to do is and you may recall that we talked about this briefly last time. I'm going to define two sets, S and G. Okay. And we are going to define S to be the set the set of maximally specific hypotheses consistent with E. And we'll get a little bit more precise about what we mean by specific in a minute. And then on the other side of that, G will be defined as the set of maximally general hypotheses consistent with E. All right, now why do we care? Well, if we're going to be doing any kind of analysis of the version space, what we need to be able to do is define the members of the version space. And naively, what we're going to find is that the number of members in that version space could become quite large. And so we want to simplify how we represent that version space. And what the sets S and G do is define the boundary of the version space. So you can almost think of this as here we have H, the space of possible hypotheses. And here is the set G, and here is the set S. And therefore the version space is everything in between. Okay, any questions about that? All right.
New page.
I need to give you another definition. But one thing to notice so far is even though I identified where the inductive biases relate to these definitions, you'll notice that so far the definitions don't directly use either one. They just say we have some way of representing the hypothesis space and we have some way of bounding the version space. All right. So let's let hi and hj be Boolean valued functions defined over x. Now let me pause for a second. Notice that right off the bat, as soon as I said these were Boolean valued, I have now imposed a representation bias. One of the things I want you to take away from this, though, is that you can come up with a similar definition to the one I'm writing now with any representation that you want. This just happens to be one of the simpler ones. All right. So from here, then we say that hi is more general than or equal to hj, which will denote hi greater than or equal with a subscript g, hj, if and only if for all examples oh, do I want to use x or do I want to use e? I'm going to keep it to e for now. For all examples in that data set e, hj of x equal to 1 implies hi of x is also equal to 1. Now notice that since we're using implication here, it doesn't say anything about going the other direction. So to decipher this a little bit more, when we go back and look at the or equal to part of that definition, then we can reverse the implication, where hi of x equal to 1 will also equal hj of x equal to 1. If the reverse does not hold, then all we can say is hi is strictly more general than hj. Okay, so we can restrict to more general than as follows, where we have hi more general than or equal to hj, and I left off the x, just if that bothers you, you can plug it back in, and hj is not more general than hi. Okay. Why do we care? We have to go back and consider those definitions of S and G. So from this, we can now rewrite S a bit more formally as the set of all hypotheses in our hypothesis space such that S is consistent with E and there does not exist an S prime in H such that S prime is strictly more general than S and it's consistent. So what this particular rule allows us to do is say that this is the most specific, or one of the most specific hypotheses within the version space. Because if you were to go more specific than that, what you would find is it's no longer consistent. And we can define G using a parallel structure. Where again, we're assuming that G is a member of the hypothesis space that's consistent with the data. And there does not exist a G prime in H such that, oh, I've got that backwards. Sorry. Hold on. This might be the question that's being asked. Should be S more general than S prime. Because down here, this is G prime more general than G and consistent. So Elijah, did that answer your question? Because I had the notation backwards.
I was talking about when you said we can restrict to more general than as follows. Like, why do you need to have that second requirement instead of just the first one by itself?
No, it doesn't, because the first one still allows equality, where the second one says they're not equal.
Oh, okay. That makes sense. Thanks.
All right. All right, so now I have defined the version space using these Boolean valued functions with our definition of the more general than relation. And those two sets in combination give us the version space. Okay, so how are we doing on time? 5 minutes. What I would like to do kind of quickly, although I got bitten the last time I did this quickly, so we'll see. We'll just see what it takes. I want to show you a learning algorithm based on this idea that helps us find the version space. Let's just jump to that algorithm. So this is it. It is called the candidate elimination algorithm. And the way it works, and this is completely different from what you have seen before. It does not look anything like Winnow. It does not look anything like naive Bayes. And the primary difference that we're going to see here is that with both Winnow and naive Bayes, we are using the data to learn exactly one hypothesis. Where what this does is it learns the version space, which means it learns all consistent hypotheses. All right, and the way it does that is it starts by initializing these two sets, S and G, to be maximally general and maximally specific. And notice that in those lines 2 and 3, it says nothing about consistent with the data. So another way to read that is that the set G is basically more general than any hypothesis in the hypothesis space. And then the set S being more specific than any hypothesis in the hypothesis space. And so what that does is it brackets the entire hypothesis space. And then what candidate elimination does is it looks at each data point one at a time. It does not iterate in this case. In fact, you'll see in a minute that it doesn't have to, and eliminates candidate hypotheses from H by updating those boundaries of S and G. All right, so looking at this, you'll notice that starting in line 4, we've got this loop that loops through the example or the training data set E, and you'll see we only loop through once. The first thing that we do, and we're assuming this is a 2-class classification problem, the first thing that we do when we come inside that loop is we look at the current example and we decide, is that example a positive example? Think A1 in the Bayesian decision theory sense, or a negative example. Think A2. This is supervised learning, and this is a labeled data point, so we can look directly at the label and say, oh, is this positive or is it negative? So if it's a positive example, dropping inside that if block between 6 and 11, the first thing we do is we take any hypotheses that currently exist in G that are inconsistent with X, and we remove them. Because if they're inconsistent, we already know that the generality is essentially getting us into trouble. And we cannot make it any better by specializing. All right, so that's all we have to do with G for a positive example. All of the work is done with the specific hypotheses. So now we look at the set of hypotheses in S. And if any of them are not specific or are not consistent, we are able to generalize them to the point where they become consistent. So how do we do that? First thing, we're going to remove the inconsistent hypothesis from our set S because it's not consistent. But then we're still going to work with that by then generalizing that hypothesis to make it consistent. And now, once we're done with that, we can compare back to the hypotheses in G, and if there are any that are more general, then we can remove, well, if there are any in S that are more general than G, we remove it because we've now crossed the threshold. We've crossed the boundary. When you look on the negative side, it's just the flip side. So again, the first thing we do is we look at S and remove anything that's inconsistent. And then for G, what we do is we specialize to make it consistent with the negative example. How do we make something consistent with a negative example? We make it so that it does not match that example. And that's why we can work on the G side. That's the candidate elimination algorithm. We're basically out of time. So what I'm going to do on Friday is I'm going to take this algorithm and I'm going to walk through a simple example so that you can see it in operation. And then we're going to move on to take this idea of aversion space and develop a theory that allows us to estimate what is called the sample complexity of a hypothesis space relative to some problem space, where in a nutshell, the sample complexity answers the question, how many data points do I need to learn this concept? So it is a computational complexity question. And again, we'll reevaluate this on Friday, but I'm pretty sure I will not get through everything, which means I will be pushing the quiz to next week. And the complication there is Monday is a holiday, but we'll figure that out. All right, so with that, let me pause and see if there are any other questions. All right. Well, thank you very much. And we will see you on Friday.